Okay, section 5.1 sequences. So there are three things in this section that we're going to talk about. The first is some definitions and summation notation. The second is product notation for repeated products. And the third and final is we're going to look at some factorial stuff and n choose R. So this section is nice because for almost all of us, actually, we've all been through Calc 2, so for all of us, we've seen sequences before. So the first two things, definitions and summation notation, definitions has an S, and summation notation, we should all be familiar with that from Calc 2, from sequences and series. Product notation, depending on who your professor was, maybe you saw it, maybe you didn't, but it's real straightforward. And then factorials, hopefully we've seen factorials before, and n choose R. You may have seen n choose R. You see it in calculus or in pre-calculus, but we don't usually call it n choose R back in that class. So let's just refresh ourselves with the definition of a sequence. So a sequence is nothing more than a set, a set of elements in a particular order. Now we're used to thinking of sequences being defined by a general term, but just know as a little reminder that sequences can be as abstract as we want them to be. They just have to be a set of things with an order to it. And that order can be defined by a general term in a mathematical equation. It can be defined by an inequality, or maybe it's just defined by a couple sentences. So let's look at a little example, refresh ourselves on sequences, maybe a couple examples of some of the stuff that we're used to seeing. So the sequence A sub k, remember this is our notation for sequences. It's the curly braces to denote a set, and the A sub k denotes an order, A1, A2, A3, and so on. They are all ordered up in that way. So this sequence is defined by its general term, A sub k equals k over k plus 1, where k is greater than or equal to 1. So remember, every sequence needs to have, if it's going to be defined by a general term, it's got to have k greater than or equal to 1, because k is an index number in this notation, so we don't start counting at 0 for sequences most of the time. If you do, then you'll be told here. So we're just going to compute the first 5 terms. So go ahead and pause the video, write out your first 5 terms, and then double check it with my answers. All right, so A1, I'll write out in extreme detail here. K is 1 now, so it's 1 over 1 plus 1, which is 1/2. Then A2 is 2 over 2 plus 1, or 2/3. A3, 3 over 3 plus 1, or 3/4. A4 is 4/5, and A5 is 5/6. So just some simple sequence work, finding terms. You're going to do a little bit of this in the homework. The next example we're going to look at is we're going to find the sequence C sub j is defined by Cj, its general term, equals -1 to the j for j greater than or equal to 0. And again, I want you to find the first 5 terms. So here, like I said up here, if we start at 0, you need to be told that. Don't ever assume. If there's nothing there, you assume you start at 1. Because when you start counting, you count 1, 2, 3. So C1, oh, that's just a negative. That should be -1 to the j there. C1 is not our first term. C0 is our first term. -1 to the 0 is 1. C1, -1 to the first is -1. And C2, -1 squared is 1 again. C3 is -1. C4 is +1, -1 to the 4th power. And so we have our first 5 terms. And if we were in class, I would ask you what kind of sequence this is, and you would all emphatically tell me this is an alternating sequence. Alternating sequence. Remember, just a little review, alternating flips between positive and negative and back again. So every other term will be a different sign, or will be the same sign, but consecutive terms will have opposite signs. Positive, negative, positive, negative, positive. So we have our regular sequence, we have an alternating sequence, and then we're going to continue looking. One more example here. One more? Two more? One more before we jump into the next thing. And that is probably what you would most often think of when you think of sequence problems. And that would be finding the general term. So we're going to find the general term for 1, -1/4, +1/9, -1/16, +1/25, etc. So remember, as I said in the last example, if you're not told that it starts at 0 or some other index number, you get to assume that this is A1, A2, A3, A4, A5, and so on. And so, again, this is a review here. So you're looking for a link between your k value and your sequence value. So 1 is 1, 2, there's a -1/4, 3 is a 1/9, 4 is -1/16, so on. So most of you probably noticed that we have over k squared for each of these. And you can think of 1 as 1 over 1 if you want to. 1 squared 1, so on and so forth. And then here we see we go positive, negative, positive, negative. So we know that it's an alternating series. We know it's going to go, it's 1 over k squared, then -1 over k squared, then 1 over k squared, and so on. So what we need is to pick the -1 power. It's to something, and it's got to rely on k. That makes it go from positive to negative. So if it's 1 is the positive version, we know -1 to the first would be negative, so we need to either up this by 1, k plus 1, over k squared, or we could similarly decrease it by 1, so instead of k plus 1, we do k minus 1 over k squared. These are the two ways to change the sign from the traditional, when it's an even index, we would have -1 to the k would be positive, whereas now we want the even indices to be negative. So either k plus 1 or k minus 1. Either of these is fine. Excuse me. All right, so you're going to have some homework problems. Again, all the sequence work should be reviewed from Calc 2. I know it was everyone's favorite part of Calc 2 was sequences and series. So speaking of series, the next thing we're going to review is summation notation. Notation. That was a long pause. So remember, if m and n are integers and m is less than or equal to n, then we have the capital sigma, k equals m, and on top, a sub k. This is equal to a1, well, in this case, am plus a m plus 1 plus a m plus 2 plus dot 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 until we get to an. It sums all of the index terms starting at m going up to n. And this is a series. Series, of course, being repeated addition. So again, we did a lot in series or with series in Calc 2. So you should be familiar with series. You can bone up on your series properties from your old Calc 2 notes or Calc 2 textbook. So just want you to compute the sum if a1 equals -2, a2 equals -1, a3 equals 0, a4 equals 1, and a5 equals 2. And we're going to do 3 of these. We're going to have the sum from k equals 3 to 5 of a sub k. The sum from k equals 1 to 2 of a sub k. And the sum from k equals 2 to 4 of a sub k. So please do pause the video here and just work out the answers on your own. Again, we should be familiar enough. Great, you pause the video, you have your answers. The sum from 3 to 5 is 3. The sum from 1 and 2 is -3. And the sum from 2 to 4 is 0. And that's just adding the specific terms. So in this last one, you add a2, a3, and a4, -1 plus 0 plus 1. Okay. So now, let's try another one. Again, you should be doing these on your own. So I would like you to compute the sum from k equals 1 to 5 of k squared. And then when you finish with that one, compute the sum from I equals 0 to n of -1 to the I over I plus 1. Okay, great. You have your answers. If you sum the squares from 1 to 5, 1 plus 4 plus 9 plus 16 plus 25, you get 55. And here I'll work this out a little bit. Because we're going to a generic n, we're doing 1, the first term, which is 0, -1 to the 0 is 1, over 0 plus 1 is 1, plus, now we have -1 to the first, that's going to be -1 over 2, it's going to flip back to +1 over 3, plus -1 over 4, plus dot dot dot, all the way down to -1 to the n over n plus 1. And this would be our final answer here because we don't know what n is. So we just leave it like this. And we don't know what sign negative 1 to the n will take. So we leave it as negative 1 to the n. So just some basic summation notation expansion. So the next problem we're going to work on is the other common thing with series, and that's expressing a series. So express the sum in summation notation, or in sigma notation. I didn't say that. Summation or sigma notation, but you all do that anyway. And our sum will be 1 over n plus 2 over n plus 1 plus 3 over n plus 2 plus ... all the way to n plus 1 over 2n. So the nice thing is when you are forming a summation notation, a sigma notation, our general term here does act like a general term. So you can imagine the sequence of all of these lined up. And so we need a sub k to equal this general term, so k plus 1, over 2k. But that's not going to work, this 2k, because this needs to be n plus 1, n plus 2, all the way to 2n. So what we want to be thinking about is another way to make this work. And if we are constantly adding, the only way to get to 2n from adding numbers to n, because it's always n plus something, if we are always adding, then as you all have probably guessed, the correct way to do that is to add n. So instead of 2k, we'd have a sub k equals k plus 1 over n plus k. Because this n is fixed, we are always adding to n, regardless of what that number is. So our summation then would be the sum from k equals, we add nothing here, so now we know we need to start at 0, up to n of k plus 1 over k plus n, or n plus k. I decided to change it around. And that's our summation. So the next couple examples, the next two, are little tricks that you have seen before, but I just want to remind us how they work. So in this example, we're going to separate the final term from the given series. And our series, we're going to do 2 of them. We'll have the sum from I equals 1 to n plus 1 of 1 over I squared, and the sum from k equals 0 to n of 2k plus 2 to the n plus 1. Also, yes, I know that I just wrote separate. Oh, and this one, I'll get to that in a second. So don't pause the video here. I mean, pause it for part A, and then when I explain something for B, pause it for part B. So in part A, we are separating the final term from the given series. So our final term is the n plus 1 term. So you can think of peeling off that last n plus 1 which leaves the series only going to n. It still starts in the same place, and we still have the same rule for the general term. Only now we add a 1 over n plus 1 squared, because that would be the last term. So we've peeled that last piece off. So in part B, we're not actually separating. So in B, combine into one series. So we're kind of doing the opposite. And so again here, I want you to pause, try part B, and know that you're going to be going backwards from here to here. Great, you did it. So in part B, this becomes our final term. You have to make sure that your two pieces are of the same format, so the 2 to something, 2 to something, so we can definitely pull this inside the summation. So we have the sum. It's not going to change its starting point. It changes its ending point up to n plus 1 now, and still 2 to the k. So these are two tricks that we're going to use a lot in this chapter for our proofs. This chapter's proofs are primarily induction proofs. And so being able to do this, either peeling the final term off or forcing a term inside of a summation, will be very useful to us. Okay, so one more example here. So we're looking at 1 over k minus 1 over k plus 1. And we're looking at the sum. So if this is our term, we're going to look at the sum from k equals 1 to n of this term. So again, you should have seen this in Calc 2. It's a very famous type of series. So what we're going to do is expand this out. So we have 1 over 1 minus 1 over 2 plus 1 over 2 minus 1 over 3 plus 1 over 3 minus 1 over 4. And this continues, dot, 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 until we have 1 over n minus 1 minus 1 over n, and then plus the last term, 1 over n minus 1 over n plus 1. So you can see that every touching term, this will cancel with the 1 over 4 that's here, this will cancel with the 1 over n minus 1 that was preceding it, this minus 1 over n cancels with this 1 over n, and all that's left is the fact that the sum, k equals 1 to the n, of 1 over k minus 1 over k plus 1 equals 1 minus 1 over n plus 1. And those of you who recognize this know this as a telescoping series. Because you can take the long series of additions and, just like one of those old telescopes that you see on like pirate movies, squish it down to this nice compact form, or spread it back out if you need to. It's got that motion. So again, this is a series that you want to be able to recognize. It's always going to have this form. You have to have the same thing here as you do here, and the denominator needs to increase by exactly 1, separated by subtraction. So again, this example and the last two are little properties, little things that you have seen before. Every Calc 2 class should cover these things when they do their sequences and series chapters. So that should be most of the review. This next little bit here is product notation. Now you may or may not, as I said at the beginning, have seen product notation before, depending on your professor. Some cover it, some don't. So if m and n are integers, and m is less than or equal to n, this big old giant looking pie, k equals m to n of a sub k, equals the product a sub m times a sub m plus 1 times a sub m plus 2 times dot 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 all the way to a sub n. Just like summation notation with the capital sigma, the big pi symbol means multiply everything. So I'm going to give you, probably let's just do 1 here. Because it's repeated multiplication, it works just as you'd expect it to. So try computing the product from k equals 1 to 5 of k. Pause and do this. Great job. Thanks for pausing. So this is nothing more than 1 times 2 times 3 times 4 times 5, which is 120. And some of you go, isn't that a factorial? Yes, this is how we define factorial. So we're not going to do too much with repeated products. You're going to see them. We're going to use them. I just want you to have seen it in case you haven't. But we do have some properties for products and sums. Most of these should be review. Products slash sums. At least all of the summation properties we should have seen before. So the first one is the sum from k equals m to n of a sub k plus the sum from k equals m to n of b sub k. Since they both have the same starting index and the same ending index, we can combine this from k equals m to n as one summation of ak plus bk. One big addition problem plus another big addition problem is the same thing as one slightly larger addition problem. And the second property, C times the sum from k equals m to n. I wrote a little too big there with my summation of ak. This is the distributive property, so C times all of these constants, this big addition can be combined and sum from k equals m to n of c times a sub k. Because the c is getting distributed to every single term. So we can combine this. Again, you definitely should have seen these two things in Calc 2. So our next property is a product property. So the product from pi k equals m to n a sub k times the product from k equals m to n of b sub k is equal to the product of k equals m to n of ak times bk. Put those in parentheses. So again, these are just some properties that we'll be using when we start doing induction proofs in a couple sections. And so we want to be familiar with them. Okay. So the last couple things before we take a look at factorials and choose are, and by last couple I mean one thing, we are looking at probably the most important thing that you did in Calc 2 with series, and that's re-indexing a series or a sequence. So we are going to transform the following series using the reindexing, or I think this book will call it the change of variable, same thing. J equals k plus 1, and our series is the sum from k equals 0 to 6 of 1 over k plus 1. So if you have taken differential equations with myself or with someone else, you'll know that this is a huge part of solving differential equations, is working with series and reindexing. If you haven't taken differential equations yet or are taking it, you will soon learn that this is a really big deal. So we need to reindex, and so you want to think about when k is 0, j is 0 plus 1 or 1. When k is 6, j is 6 plus 1 or 7. And so that gives us new bounds for the start of our sum and the end of our sum. And the only other thing is to substitute is the j directly for the k plus 1. So the sum from k equals 0 to 6 of 1 over k plus 1 equals the sum from j equals 1 to 7 of 1 over j. So it's a reindexing. These summations are equivalent. This one's in terms of k, this one's in terms of j. And we can redefine our index any way we want. I just happen to use this one. But anytime you're reindexing or changing variable, you want to make sure that you look at your lower and upper bounds for your summation, and make sure that you are switching any of the old variable to the new variable. And if we wanted to go back, you would see that j, not up here, you would see that k from here down is j minus 1. And so now we can convert back. When j is 1, k is 0. When j is 7, k is 6. And j can get swapped straight with k plus 1. But you can use your equation, your change of variable equation, to switch things around. So there'll be some homework problems that have you reindex things. And we want to get good at that. Okay, so let's talk factorials and n choose r, and that will take us to the end here, maybe 5 or 6 more minutes. So factorials. So factorial is the exclamation mark symbol, and everyone should have seen factorial before. Just a reminder, it's n times n minus 1 times n minus 2 dot 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 all the way down to 3 times 2 times 1. You just multiply the starting integer with all of the preceding integers that came before it. All right, so for example, we'll just do a couple here. We'll do the common ones. So 0 factorial should equal 1. And I'm going to digress a little bit here. This is usually the place where people ask, why the heck is 0 factorial equal to 1? And the best answer I can give you is that factorial is very ubiquitous with counting problems. And if you look at the factorial as counting up the number of integers and then multiplying them, there is only one integer, 0, but there's nothing to multiply 0 by. Because there's nothing less, there's no n all the way to 1 that's less than 0. 0 is 0. So that's the best reasoning I can give you, is that it's a counting principle first and foremost. You count up how many integers there are, and then you multiply all of those integers together. Well, there's one integer here, 0, but there's nothing to multiply by. So our definition fails, just for 0. For every other integer, it's fine. So we want to know that 0 factorial is 1. 1 factorial is just 1. 2 factorial is 2 times 1, or 2. 3 factorial, 3 times 2 times 1, or 6. 4 factorial, we're going to get clever here, is 3 factorial times 4, or 6 times 24. Whoops, gave it away. 6 times 4, which is 24. 5 factorial is 4 factorial times 5, or 24 times 5, which is 120. And 6 factorial is 5 factorial times 6, which is 120 times 6, which is, I could do math, 720. And this is the end of the factorials that people generally know off the top of their head, up to 6 factorial, because we can construct them in this kind of recursive fashion, looking at the last one, 1, 2, 6, 24, 120, 720. But in case you were curious, 7 factorial is 5,040. It's just 720 times 7. 8 factorial is 40,320. And 9 factorial, this doesn't really look like an exclamation mark, 9 factorial is 362,880. Factorials get big real fast. So this is why I say that 6 factorial is usually where most people know to. Some people know 7 factorial, but I rarely encounter anyone who knows 8, 9, or higher off the top of their head, because you don't need to. If you know up to 6, you can easily find these 3 and anyone after that. So, some common factorial work that we see is simplifying factorials. Because it's repeated multiplication, our calculators, even though they're real good at calculations, fail with large factorials because you're multiplying really big numbers. Right? 10 factorial is 3,628,800 because you're just multiplying this number by 10. And so we want to make sure that we can simplify factorials as much as possible. And that usually follows a very specific simplification process. So we'll do 2 of these. We'll do, let's not do that one first. Let's do 5 factorial over 2 factorial times 3 factorial. So we're always going to look to cancel out as many of the factorials as we can. So 5 factorial is 5 times 4 times 3 factorial over 2 factorial times 3 factorial. And so these can be canceled. And we end up with 20 over 2, or 10. Also, I hope you paused and did that yourself. So this is the kind of the process you want to be thinking about when you're simplifying factorials. Let's do one with variables, because those are what we're going to see the most when we start doing proofs. My goodness. I didn't need to write example again, but I did. Okay, so let's do n plus 1 factorial over n factorial. So you can think of n plus 1 factorial, n plus 1 times n factorial, all over n factorial. And just like we did up here, cancel out the largest thing, and this is equal to n plus 1. You know what, let's do one more just for fun. Let's do n factorial over n minus 3 quantity factorial. So sometimes we have to get clever with how we expand. So we have n times n minus 1 times n minus 2 times n minus 3 factorial all over n minus 3 factorial. And something to just make sure that we're aware of, your factorial symbol, the exclamation mark, only affects the thing right to its left. So it affects these parentheses, parentheses close. This is just regular multiplication now. So that means that this factorial is not talking about these 3 things. It's just talking about the parentheses that it's touching, which is just the n minus 3. So these cancel away, and we have n times n minus 1 times n minus 2. And that's nothing more than n cubed minus 3n squared plus 2n, expanding that out. So that's kind of the thinking that we want to have when we're simplifying factorials. Whoops. And why do we want to simplify factorials, you ask? Well, that's because we have n choose r. So this is n choose r. So the symbol for this is a stacked parentheses with n over r. It's really easy to want to write the division bar here. I do this all the time. Make sure that you don't, because it's not n over r, it's n choose r. And so we read this as n choose r. So this is 0 is less than or equal to r is less than or equal to n is the requirement. And what this is the number of subsets of size r that can be taken from a set of n things, or n elements. So you can think of this as how many ways can you divide n by r? So let's say I'm making groups for group work, and I want each group to have r people, and we only have n students in the class. There are only so many combinations that I can make. I can make exactly n choose r different combinations. And n choose r is defined multiplicatively as n factorial over r factorial times n minus r factorial. And so this is why we want to be able to simplify factorials this way, because this calculation can get pretty intense. And if you don't simplify, a lot of times your calculator just can't do this because it's doing too many multiplications and it runs out of memory. So to end this, I lied, it wasn't 5 or 6 minutes. To end this section here, I'm going to give you 3 n choose r's to calculate, 8 choose 5, 4 choose 0, and n plus 1 choose n. So pause your video, calculate these out. Now you've unpaused, and the answers, because you're just setting this expression up and simplifying, are 56, 1, and n plus 1. So just to talk about what that means, the number of groups of 5 that I can make out of 8 people, there are 56 of them. The number of groups with 0 people that I can make out of 4 is 1, because there's only one way to make a group with 0 people. That's none of them. And the number of groups with n people that I can make out of a total of n plus 1 is only n plus 1 people. So that's the end of 5.1. I'll be starting 5.2 momentarily.